We're going to expand even further on our understanding of resistors in series and parallel, and we'll actually have analyze circuits that have combinations of series and parallel resistors. Again, this is the review of the resistors in series. Remember, resistors in series, the current is constant. The total voltage is the sum of individual voltages. The same thing with the equivalent resistance. The equivalent resistance is the sum of the individual resistors in series. These are three important equations to know. And always remember Ohm's law, V equals IR. For series and parallel, the equations to remember are that the voltages are the same. Because all of these resistors, the left side of each of these resistors is connected to the positive terminal of the battery, and each of the right side of these resistors is connected to the negative terminal of the battery. That means the voltages across each of these resistors is the same. The currents, though, are summative. This total current, or equivalent current, goes into this point, or node, and it breaks up into three different currents. This total current is the sum of those three currents. When these three currents come out this other side, they add together to get this total current again. The current here and the current here is the same, but there's three different currents in each of those branches. So the total current, or equivalent current, is summative. The equation for the equivalent resistance is this equation. The inverse 1 over the equivalent resistance is equal to sum of the inverse of the resistors. And make sure when you solve for this equivalent resistance, you have to invert this sum. Let's see how we can apply that to solving problems. Start with easy and then get a little more complex. We have two 100 ohm resistors. You should draw this circuit connected to a 24 volt battery. Of course, the current always flows from high potential to low potential. The current is going this way. There's only one current in the circuit because there's only one path for the current to go. And we want to determine this current. We want the total or equivalent current going through that circuit. Well, the way we do this is we get the equivalent resistance first. The equivalent resistance in series is the sum of the resistors, R1 plus R2. And so the equivalent resistance is 100 ohms plus 100 ohms. It's nice that these are the same resistors, makes it nice and easy. That's the equivalent resistance of 200 ohms. We then use Ohm's law, V equals IR. This is the equivalent resistance, and the equivalent resistance will give us the total current. And this is the total current. Well, the total current is the current through each resistor. There's only one current, so that is the total current. The voltage, the 24.0 volts, total current times equivalent resistance of 200 ohms. We get that total current to be 0.12 amps. Now, the thing to remember, when we get this equivalent resistance, we add those two resistors up, that's if we replace those two resistors with just one resistor, it's equal to 200 ohms. So this equivalent resistance is 200 ohms. So if we replace those two with one resistor of 200 ohms, and we get that current of 0.12 amps. Now let's take a look if these were in series. So again, to draw this circuit, we have two 100 ohm resistors in parallel, connected to that 24 volt battery. And we want to determine this total current through this circuit, or through each resistor. Now, we want to determine, I'm going to call this current 1, and we want to determine current 2. So this total current, or equivalent current, hits this point right here, and branches into two different currents. We'll call this one I1, going through resistor 1, this one I2, going through resistor 2. Now, the thing in parallel that is constant is the voltage, because both these resistors are connected directly to that battery. So we can use Ohm's law, V equal to I1 R1. The voltage is 24 volts, so we can very easily determine the current going through this resistor. We're going to do some other things once we finish the currents up. This voltage is 24 volts. That's the voltage going across this R1, that 100 ohm resistor, is equal to I1 times R1, which is 100 ohms. This is I1, not I2, this is I1, and that's equal to 0.24 amps. We can do the same thing for I2. The voltage is equal to I2 times R2. The voltage is the same, 24.0 volts. I2 and R2 is 100 ohms. And we get I2 also equal to 0.24 amps. The reason these currents are the same is because the resistors are the same. If the resistors were different, the currents would be different. The smaller the resistor, the more the current would go through that branch of the circuit. Now let's do a couple other things. Let's figure out the equivalent resistance of this. What is that equivalent resistance? Well, the way we do that is we take 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2. We put these values in, 1 over the equivalent resistance equal to 1 over 100 ohms plus 1 over 100 ohms. If we solve for this, we'll get this equivalent resistance to be 50 ohms. 1 over 100 plus 1 over 100, and we invert that answer, and we get 50 ohms. So the good thing to remember is that the equivalent resistance of resistors in parallel is always less than the smallest resistor in parallel. This will always be, the equivalent resistance will always be smaller than the smallest resistor connected in parallel. It's a good thing to remember. Now, let's take a look at some other things we can, kind of interesting to see about this. The total current is what? Is equal to the sum of the currents. So this total current is equal to I1 plus I2. That total current is going to be 0.24 amps plus 0.24 amps. Of course, we get that total current to be 0.48 amps. Another way we could get the total current, again, is if we take the voltage, again, if we take these two resistors in parallel, we can replace those two resistors in parallel with only one resistor at 50 ohms. So these two resistors can be replaced with one 50 ohm resistor and we get the same effect. Let's see if that works. That voltage is equal to the total current times the equivalent resistance. The voltage is 24. Sorry. Voltage is 24.0 volts. The total current equivalent resistance is 50 ohms. And if we take 24 divided by 50 ohms, you get a total current of 0.48 amps. The same thing. Right? So that's those are the simplest series and parallel circuits. Let's see if we can combine series and parallel resistors. Let's take a look at this next problem. How much total current is drawn from the battery shown in the circuit? Now this is what's happening. This is the battery and the current. This is the positive terminal, this is the negative terminal. The current flows from positive and negative. I'm going to call this I1. You can call it I total if you want to. I'm going to call it I1. This I1 goes through this 400 ohm resistor. All that current goes through this 400 ohm resistor, but when it reaches this point here, it splits up into two different currents. One current going this way, I'm going to call this I2, and one current going this way, I'm going to call this I3. When these two currents reach back here, they again form I1, the total current going through that circuit. So how do we figure that total current? Well, we need to determine the equivalent resistance of this entire circuit. We're going to do that first. So we have these two resistors in parallel, so we can determine the equivalent resistance of those two resistors. There's going to be 1 over Req equal to 1 over 500 ohms plus 1 over 700 ohms. We get that equivalent resistance to be 292 ohms. So again, this is if we replace this resistor. Let's do that. Let's say this is the 400 ohm resistor. And now we have replaced this parallel part of the circuit with just one equivalent resistance of 292 ohms. Notice now that equivalent resistance of the parallel resistors, this is 292 ohms, that's in series with this 400 ohm resistor. So now the equivalent resistance is the sum of those, which is 400 ohms plus 292 ohms. That equivalent resistance is going to be 692 ohms. What's the total current? Going through there, we then use Ohm's law. V equals I1 times the equivalent resistance, because this I1 goes through this one resistor. So now what we have is all three of those resistors are replaced with one 692 ohm resistor that's connected to this 12 volt battery. We use Ohm's law. This is I1 still, that's the total current going through there. There's going to be 12.0 volts equals I1 times the equivalent resistance of 692 ohms. We get that I1 to be 0.0173 amps. That's the total current going through that circuit. Now, let's look at this next part, part B. What is the current going through the 500 ohm resistor? Well, this is the 500 ohm resistor. So how do we do that? Well, let's take a look at, let's kind of go backwards from where we came. Let's go back up to where we have this part of the circuit, where we have a 400 ohm resistor and a 292 ohm resistor in series. This 692 ohm resistor is broken up into two resistors in series. Remember, series, the current is the same. So this current right here that we got for this entire circuit, we break this into series, the current hasn't changed. It's in series, the current is constant. So this is the same current going through this 400 ohm resistor. So then, I'm going to redraw this down here. What we have is this is the 400 ohm resistor, and this is the 292 ohm resistor. The current going through here, this current, is 0.0173 amps. If we know the current, using Ohm's law, we can get the voltage across this 292 ohm resistor. But remember, we're going to break this 292 ohm resistor. This is the 292 ohm resistor. We're going to break it into two parallel resistors. And it's the voltage that's constant. So we're going to use E equals IR, Ohm's law, always a useful thing. And so this is the voltage. The current is 0.0173 amps. The equivalent resistance is 292 ohms. We get this voltage going through that parallel branch to be 5.05 volts. Now this is what we have. We're going to take this 292 ohm resistor, we're going to break it into the 500 ohm resistor and the 700 ohm resistor. So this 292 ohm resistor is now broken up into these two parallel resistors. Remember, in parallel, the voltage is constant. This is the voltage across this. We break it up in parallel. The voltage is the same. So this is the voltage across the 500 ohm resistor. And we want to know the current. We're going to call this current I2. That's up here. This is I2 going through that 500 ohm resistor. The voltage is the same, so we use, again, Ohm's law, V equals I. So it'll be I2 times the resistance of the 500 ohm resistor. The voltage, we calculate, would be 5.05 volts. I2 is what we're solving for, and that resistance is 500 ohms. We get that current to be 0.0101 amps going through I2. Now, let's make this even more interesting. Let's make it a little more complicated. There's this in the circuit. Go to the next page. And so now we have this circuit. We have multiple resistors in here. And what we want to do, part A, is determine the total current drawn from the battery. Now here's the battery. This is the equivalent resistance is equal to 9.0 volts. Sorry, that didn't come out right, but that's 9.0 volts. We want to determine the total current drawn from this. This is the current going through the circuit, going this way. And then once this current reaches here, it's going to break up into this branch, this branch. Once it reaches here, it's going to break up there and there. They all come back together and form that. But the way we determine this total current is the first thing we have to do is determine the equivalent resistance. This is kind of like doing a long algebraic problem where you have parentheses inside parentheses inside parentheses. You do the parentheses inside, the closest ones inside first, and you gradually work your way out. Well, that's kind of what we're going to do with these resistors that are in series and parallel. So the first thing we're going to do is we're going to determine this equivalent resistance of those two parallel resistors. So 1 over Req will be 1 over 8, this is 8.0 ohms. Plus 1 over 4.0 ohms. we get this equivalent resistance to be 2.7 ohms. So what this part is now, this is a 6 ohm resistor now in series with this 2.7 ohm resistor. And so now we can determine the equivalent resistance of this. So all of this right here is that. So now we're going to take that equivalent resistance. This will be 6.0 ohms plus 2.7 ohms. We get that equivalent resistance to be 8.7 ohms. So now what we have, all of this is an 8.7 ohm resistor, and it's in parallel with this resistor up here. So we're actually going to have something like this. This is going to be a 100 ohm resistor, and this is an 8.7 ohm resistor, and those are going to come in contact with this. We don't know what this is. We know what this is, but we're going to wait to do that part right here. But these two are in parallel because the current comes in here, the current comes up here and breaks into those two parts, and those two are in parallel. So we can determine this equivalent resistance in parallel. So 1 over REQ equal to 1 over 10.0 ohms over 1 plus 1 over 8.7 ohms, which is 7. We get this equivalent resistance to be 4.65 ohms. I'll go ahead and put the 2 places past the decimal. So now what we have is all of this up here, all of this is a 4.65 ohm resistor. If I redraw the circuit just a little bit, what we have now is all of that top branch is 4.65 ohms. It is now in series with this 5 ohm resistor, and it's in series with this internal resistance of 0.50 ohms. So notice there's only one path that current can go through this. All those resistors are now in series. So now we add all those up and we get this equivalent resistance to be 0.50 ohms plus 4.65 ohms, plus 5.0 ohms, kind of crushing that together. We get that equivalent resistance to be 10.15 ohms for the equivalent resistance. Remember, we're trying to get this total current. So now we use Ohm's law. This is, since now we're using this internal resistance, this is the EMF, or V, is equal to IR. This is going to be 9.0 volts. Equals this current, this is the total current, times the equivalent, this equivalent resistance, this must be total current, of 10.15 ohms. You get that total current to be 0.89, we'll just put 2 significant digits here, 0.89 amps for that total current. Now there's some other things that we can do here. Because what is the terminal voltage of the battery? The terminal voltage is V. Remember, we have this equation that the EMF is equal, that the terminal voltage V is equal to EMF minus IR. Well, now we know the EMF, we're given an EMF of 9 volts, would be the voltage equals 9.0 volts minus, we now know the current of 0.89 amps times the internal resistance of 0.50 ohms, and we get that voltage of 8.56 volts, or 8.6 volts. There we go. Alright, now the fun stuff. I want to determine the current in a 6 ohm resistor. Notice where that 6 ohm resistor is, right here. We want the current going through that 6 ohm resistor. Let's see how we do that. Remember, this 6 ohm resistor is in this entire equivalent resistance of this 4.56 ohm equivalent resistance. So what I'm going to do, I'm just going to redraw that right here. This is 4.65 ohms. This is 0.50 ohms. Whoops. This is the positive terminal, that's a negative terminal, and then there is a 5 ohm resistor here. Now, let's make sure we understand. So now this is the current. This current, 8.9 amps is the current that's going through this 4.65 ohm equivalent resistance. So we can figure the voltage across this. So I'm going to take this 4.65 ohm, and I'm going to gradually break it back up, or split it apart into the resistors that form this part right here. So I'm going to determine the voltage across that 4.65 ohm resistor using Ohm's law. V equals IR. We know the current is 0.89 amps. We know that equivalent resistance of 4.65 ohms. We get the voltage across that equivalent resistance to be 4.14 volts. Now, this equivalent resistor here this is the equivalent resistance here. We got it from the equivalent resistance of these two parallel resistors, the 10 ohm resistor and the 8.75 ohm resistor. This 8.75 ohm resistor is the equivalent resistance of all these resistors in here. I'm going to break that 4.65 ohm resistor into two parallel resistors. This is a 10 ohm resistor, and this is the 8.7 ohm resistor. Remember, we're breaking this into this right here into two parallel resistors. The thing that's constant in parallel is the voltage. So this voltage is the voltage across this 8.7 ohm resistor. So if we know the voltage and the resistance, we can figure the current using Ohm's law. V equals IR. Voltage, 4.14 volts. Current, we're trying to determine. The equivalent resistance, 8.7 ohms. We get that current to be 0.48 amps. So now we're going to break this 8.7 ohm resistor. Remember, this 8.7 ohm resistor here comes from these two resistors, the 6 ohm and this 2.7 ohm resistor that we got here. This 8.7 ohm resistor comes from these two resistors here. So I'm going to break this 8.7 ohm resistor back into its 6.0 ohm resistor and its equivalent 2.7 ohm resistor. Remember, this is the current going through this 8.7 ohm resistor. We break this up into two resistors in series. What's constant is the current going through here. So this 0.48 amps, that current is the current through that 6 ohm resistor. So the current through the 6 ohm resistor is 0.48 amps. Now we could go on. Let's do a part D here real quick. Part D. We want the current through the 8 ohm resistor. 8 ohm resistor. That's really 8 ohm. This is the 8 ohm resistor right here. This 8 ohm and this 4.0 ohm is that equivalent resistance right there. I'm going to take this 2.7 ohm resistor here. I'm going to break it up into its parallel resistors, which is the 8 ohm resistor, and this 4.0 ohm resistor. And if we want the current through this resistor right here, now remember, when we break something up in parallel, the thing that's the same is the voltage. So the first thing we need to do is determine the voltage across this 2.7 ohm resistor. Well, the current is the same. The current is 0.48 amps, the same current going through the 6 ohm resistor. So we use Ohm's law, V equals IR. We want this voltage, the current is 0.48 amps. The resistance is 2.7 ohms. Sorry, 2.7 ohms. Remember, we're getting the voltage across this resistor here, that equivalent resistance right here. So then this voltage is going to be 1.30 volts. So that's the voltage across this 2.7 ohm resistor. We break that 2.7 ohm resistor into two parallel resistors. The voltage is a constant, so now you know this voltage across this 8 ohm resistor. Now we can figure out this current. V equals IR. Voltage 1.30 volts. Current is what we're solving for. The resistance is 8.0 ohms. We get that current to be 0.163 amps. Stop there. You have an assignment posted on the LMS. I think it has several problems that practice doing simple to complex circuits like this. Take a look at that, and I think there's some practice problems and an assignment. We'll stop there.